So you can start anonymously. So I cannot want to match the name with your answer. I just want to know the ballpark, you know. So, and while you're measuring, you're assessing your feeling, I'm going to talk about a couple of things from the review. Can you hear me? Yeah, I was watching my lecture and I found some issues which I would like to address. Well, for example, when I was solving this problem, I wrote 300 and I said 30. I wrote 6,000 and I said 600. You know, when I watch the movie, I can see every single thing. So again, I don't know. Maybe I just need a good night's sleep, or I should watch the movie Still Alice. Nobody knows. But anyway, these little things, not really important. This is a little bit bigger thing. When I was trying to draw a triangle and count little things without the ruler, I kind of made a little mistake, because clearly this triangle can't have the indicated sides. If this is 1, this is clearly shorter than 1, so I should have keep it drawing. This is 1. So if we have two speeds of equal magnitude, so this should be the correct triangle if you're trying to move like this. Yeah, if you're trying to move like that. It doesn't change anything else. It just, the picture has a wrong feature, and I want to correct it. Still, what matters is only this component. And this component is shorter relative to this case, so it doesn't change the reasoning. So please keep answering anonymously. And there's one more thing which I have to address. When I have been solving this problem, and first I draw this diagram, I said 12. I remember that. And it's in a video anyway. And I should have stick to that, because clearly anything else doesn't matter. If we have two objects and they interact here, if the force is 12, it stays 12 for anything. But when I started calculating, I made a very, very common mistake. And in a way, I'm glad I made that mistake, because I can point it out. When we draw a free body diagram, we have to show all the forces. And I didn't. I missed one force. And that screwed up the calculation. So which force do you think did I miss? You don't have to answer out loud, but you should be honest to yourself. You have to say it to yourself. Oh, I know. The missing force is, well, so for the bottom box, for the box at the bottom, we have force of gravity, which I used here. We have normal force. We have force of friction. And we have the force of 21 newtons due to the string attached to it. And now there is a missing force. Yeah, because there is a box above it. It touches. There is another force acting down. So I didn't take that force into the account. That's it. But I should have. So the correct calculation for the force of friction, of course, should be like this: the coefficient times the normal force, the coefficient which is 0.4, but the normal force is not equal to mg. It can't, because of that additional force acting down. See? So the normal force actually should be equal to mg plus that additional, which was equal to Okay, F normal additional. So this is the correct calculation, which should give same 12 newtons as it was before. So missing force. It's a case of a missing force. It's a new serial, with Sherlock Holmes. A case of the missing force. Remember, solve it every time. All right, it's time to see how you measure your feeling. Well, it's actually very, very, what I see here, I see it almost every time. It's very, very common distribution. So that gives me kind of peace of mind as well, that it should look like in general, for general class. So now we go to an actual question I want to ask you. We talk about work energy, so please tell me what you think. And this question is not anonymous. It's another option for you to prove your presence here. I wish I tell it every time, and nobody helped me, but I wish some computer major student would develop a software which I could use here. So I could take a picture, and the picture recognition software would immediately take the attendance. That's it. The faster, the simplest way to do that would have been, well, but I'm not familiar with software side of this idea, so I give it to you, a gift. This equation, of course, can be applied to only specific type of forces and cannot be applied to other forces. And the key is right here. Constant. If the force is constant, yes, constant force, we can apply this equation for calculating the work done by that force. But if it's not constant force, we cannot. So the force, the elastic force, the force which we generate in the spring depends on its length. So when we stretch or when we compress the spring, the force also changes. So it's not a constant force, and we cannot use that equation for the elastic force. Cannot. It violates the condition. Well, we started doing this problem, so let's just continue solution. This problem involves major forces. So what's happening is, okay, let's again do a bigger picture. That's how we are applying the force. Well, this is 60 degrees angle, this one, because it's equal to that one. And of course, we have the force of gravity. The normal force, and the force of kinetic friction. And, well, they're all constant forces. So for each individual force, if we want to, we can apply this equation. However, for the work done by gravity, easier using the second equation we've derived from the first one. So when the height doesn't change, gravity doesn't do any work. Now, for the work done by the normal force, we know it's always 0 because the angle between the force and the displacement is always equal to 90 degrees angle. So that's a simple thing. Applied force, we did it, but very quickly. The work done by applied force. Well, see, in the past, when we had to calculate the acceleration and when we had to apply to Newton's law to this problem, we usually use the x and y components of the angled force. Now we don't have to. We could have. We could have because, well, again, let's step aside for the moment. This force is equal to the sum of its components. The component which is perpendicular to the displacement doesn't do any work. Only the component which is parallel does work. So, but of course, the equation for the work, we don't want accidents here. The equation for the work takes care of this automatically. We just have to multiply the magnitude of the force, which is 14, times the magnitude of the displacement, which is 2, times cosine of the angle between the force and the displacement. Sometimes it helps to draw both arrows from the same starting point. Because, for example, if this is my force and this is my displacement, I've seen people trying to using this angle for calculating work, which would have been wrong. That's not the angle between these vectors. To measure the angle between two vectors, we have to draw both from the same point. So that's supposed to be the displacement, that's supposed to be the force, and that's supposed to be the angle theta we have to use in this equation. And now, well, wherever it is, has to be used 60. Well, the last work left to calculate is the work done by friction. That's a tricky one. Well, work done by friction, because it's a constant force, can be calculated again as the, well, we know it's supposed to be equal to the -1 because of cosine of 80 times the magnitude of the force of friction times the distance traveled. And -1 cosine of 180 times distance, which is 4 meters. Those are clear parts. So it turns out, for calculating the work done by friction, we just have to go back in time and solve the problem about forces, exactly as we did it before. So how do we calculate the force of friction? It has to be equal to the coefficient of friction times the normal force. How do we calculate the normal force? Well, again, would it be correct to assume that the normal force is equal to mg in this situation? Since I've heard both yes or no, now I want to see, would it be correct to say that the normal force is equal to mg, yes or no? In a way, this again is a review which helps us to get better prepared to the upcoming exam. In a way, it's one of the part of the reasoning. So that's why, even it's a kind of new topic, we still have to use the same knowledge we've learned before, and we're going to have to use it till the rest of this course. No is the correct answer, but some people still think wrong, and we always have to ask the question, the same question. Is there any reason for the normal force to be different? And the reasons are, well, so there is something touching. In this situation, we can assume that my hand is touching, and the vertical component of the applied force changes the normal force. So that's what we need to use here. The normal. That's all I got left. All right, it's in a movie. So the normal force, so this is equals to this plus this. So, and we have three vertical arrows. Normal force points up, force of gravity points down, and this arrow represents the vertical component of the applied force. And now we can see that the normal force will be equal to mg plus this component. And now we can calculate the work of the force of friction, which is supposed to be equal to -1. That's cosine of 180 times this. Let's calculate it. Please calculate the actual number. So the box weighs 4 kilograms. The coefficient is 0.1. The distance traveled is 2. So 4 kilograms times 10 plus the applied force, 14 newtons, sine of 60 times 2 meters. And the force, applied force, does work, which was equal to 14 times 2 times cosine of 60. Same force, so what do we get here? 28 times cosine of 60. I got 12.5 joules. Here, 14 times sine of 60 equals plus 40 equals times 2 equals. I got -104.12. Let's neglect all points. Let's round it up. Please check my numbers. Everybody makes mistakes. The difference is, what do we do about that? Yes? Perfect. So now we can immediately calculate times 0.1, the coefficient times 0.1, -10.4 joules. The coefficient of friction. So again, -1 times the frictional force times distance traveled, -1, coefficient times normal times distance traveled. Yeah. Now, we know all individual works, so what can we calculate now? Now we can calculate the total work done by all forces, the net work. And the net work will be equal to 0, work done by gravity, plus 0, work done by the normal force, plus 12.5, the work done by the applied force, plus -10.4, the work done by the frictional force. So that's going to be equal to 2.1 joules. The net work is positive. That means the object is speeding up. It's moving faster and faster. So we can apply the work-kinetic energy theorem to calculate its final speed. Well, normally we assume it starts from rest. So if it starts from rest, the initial speed is 0. The initial kinetic energy is 0. So the final kinetic energy, which is mv final squared divided by 2, well, minus 0, should be equal to that number we just got, 2.1 joules. And because we know the mass, the final speed will be equal to 2 times 2.1 divided by 4, square root of that, meters per second. That is how everything is related to everything in a situation like that. We could have calculated the final speed differently. If we know all the forces, we can calculate acceleration. If we know acceleration and distance, we can calculate the speed. Of course, the result will be the same. So it doesn't matter sometimes which approach to use, forces or energy. But in many situations, using work-kinetic energy relationship gives away the answer faster. Okay. Any questions? If you have any question at any point, raise your hand. So we've seen these equations before. This is how we can calculate the work done by gravity. This is how we can calculate the work done by elastic force. You see the structure is very similar. There is a difference, and we're subtracting two things, one of which related to the initial position and another to the final. What was happening in between doesn't matter. Only initial height and final height do matter. Only initial stretch and final. How did it happen? Doesn't care. So a force like that, a force for which work doesn't depend on what was happening. It depends only initial state and final state. A force like that has a name, a conservative force. That's a name. Conservative means the work doesn't depend on the process. It depends only on initial and final state, position. Force of friction is different. Of course, it depends on the process. If I move this box from this point to this point, and I use, well, a short distance, that gives me one amount of work. But if I do it this way, the initial and final positions are the same, but the amount of work done by friction will be different. So that's a non-conservative force. And if we use this notion, well, first we can introduce one more definition. The sum of kinetic and potential energy of an object has a name, mechanical energy of an object. So potential energy, well, depends on what's happening. If the string is attached, is this. Normally, there is also some kind of a potential energy related to a location relative to the ground. And the kinetic energy, well, always not equal to 0 for the moving object. But if we add them up all together, the result has a name, mechanical energy. a capital U is a general notation for potential energy of anything. It generally might include both possible energies, gravitational and elastic. But now we can restate the work-kinetic energy theorem. Again, it's not a new theorem. It's the same theorem written differently. But because it's written differently, it has a new name. If there is no friction, or in general, if only conservative forces are acting, mechanical energy doesn't change, never changes, stays the same, is constant. That's why this law has a name, the law of conservation of mechanical energy. Only non-conservative friction, forces like friction, can change mechanical energy. That's it. And if friction is involved, or in general, any non-conservative force is involved, but we're going to talk about friction only. So that's why I replace, it's not exactly accurate, but I replace this term non-conservative with the word friction. So if friction is involved, we have to add the work done by friction. Only friction changes mechanical energy. Only non-conservative forces change mechanical energy. So this equation has a name normally, master equation. It relates all possible energies and works involved into this situation. Kinetic energy initial plus potential energy initial plus work done by possible non-conservative forces gives us kinetic energy final plus potential energy final. This is no different from work-kinetic energy theorem. No. We can rewrite this equation. We can rewrite this equation. So kinetic initial plus potential initial plus the work done by non-conservative forces equals kinetic final plus potential final. But if we write this difference, final kinetic minus initial kinetic, what does it give us? This difference plus this. This is the work done by all conservative forces. This is work done by all non-conservative forces. So that's just literally total net work. So there is no difference between these equations. Historically, they've been derived from different perspectives, and we can use any. Doesn't matter. But there is sometimes a point of convenience. Sometimes one equation gives an answer faster, sometimes another. It is one. Thank you. All right, so if this is actual friction, if this is an actual work of friction, what should happen to mechanical energy? Well, of course, I'm not going to even ask you this question, because we are actually adding a negative number. So friction always decreases mechanical energy. So again, remember, the work done by friction always is negative. So we are adding here, adding a negative number. The work done by friction is equal to -1 times the magnitude of the work done by friction. That's what a negative number means. So friction always decreases the mechanical energy of the system. And now we've learned everything. So what's left? Now practice. So I'm going to prepare. Don't press anything yet, because you don't know what to answer. Because you have to see what's going to happen. This is what's going to happen. The whole thing is like 6, 7 kilograms, 12, 14 pounds. So, when I'm lifting it up, I'm doing the work. And now it has higher potential energy than it was here initially, right? So when I let it go, when I release it, that's how we call that potential energy potential. Yeah, we store it, but potentially it can be used, it can be transferred into other forms of energy, including, for example, kinetic energy. So it's actually a lot of kinetic energy. We can calculate. This is 4 kilogram weight, and this is about 1 meter. So so what's going to be the potential energy of this weight? Equal to? Anyone? Wrong. That's a trick question, because you don't know what the origin. You should ask, where's the origin? Maybe the origin is right here. Relative to this origin, it has zero potential energy. So that was a tricky question. But relative to the bench, yes, of course, it's mgh 4 times 10 times 1, 40. So in that situation, what's going to happen? That's what's going to happen. And of course, the result depends on the height. You see? We can, and this is actually how initially, in 18-something, I don't even remember, has been established the relationship between kinetic energy and potential energy. You can drop it from different heights, and you can see, well, you can actually measure, and you can relate how it works. But the question, my question is this. In this experiment, is mechanical energy conserved? Mechanical energy, is it conserved? And these are the possible answers. I just like doing this. I will have to edit it out. I'm sorry. I scared you. Did you have a chance to press? All right. That was a faulty can. Well, the key to this, to answer to this question is what's happening here. When we're crumbling things, there is the internal friction, of course. And if there is a friction, the mechanical energy cannot be conserved. So some loss of mechanical energy is happening due to friction between the parts of that can. Plus, you know, so there is some friction here, and some energy loss. Yeah, we say energy loss. But it's, again, a very general term. Mechanical energy decreased. But if we say about the energy as a whole, we just said in the beginning of this topic, the energy in general cannot disappear. So the total amount of energy, if we include all the forms, must be the same before and after. So if mechanical energy changes, where does that energy go? What do you think? What do you think? So almost 50-50 distribution. Well, of course, it was again a tricky question. I tricked you. In many problems we've solved before, usually we assume that we can neglect friction. But if I told you you cannot neglect friction, I would give away the answer, right? So where did it go? What do you think? So mechanical energy changed. The initial mechanical energy, mechanical energy 1, has a larger value. Where did the difference go? Anyone? If you say something, it should be louder. It's not in the no, it's no. So potential energy is a part of mechanical energy. Neglecting friction, the mechanical energy will stay the same. We will do a calculation like that. Of course, starting from now, we will be neglecting friction. So if I have a ball released and falling down, neglecting friction, mechanical energy stays the same all the way down. Potential energy decreases, but kinetic energy increases, and total balance doesn't change, but only neglecting friction. But if friction cannot be negligible, what does it go? All right, I gotta start asking questions. What do you think? No. The can also actually doesn't move in the end. What do you think? So what do you think now?
I'm still confused.
Yes. Of course, everybody uses every time. If your hands are cold, what do? That's what you do. Because friction, getting transferred into what we call heat, that's one of the future topics. And you know, if you rub it long enough, strong enough, you can feel the temperature rises. So there is another form of energy. Of course, this experiment tells us a very important fact. It might seem that energy changes, total energy changes. And in physics, it happened several times before. Like, they thought, okay, the law of conservation of energy doesn't work anymore. But turns out, people succeeded to find another form of energy and another form of energy. So, and this is an example of a situation when mechanical energy is not conserved, but the total energy still is conserved. So this difference actually is equal to amount of heat energy. So everything gets slightly warmer, even the can. We cannot feel it, but if we had very sensitive measuring devices, we could measure the change in the temperature. Well, now this is a specific situation when we neglect the friction. 100 ball is released from rest. Like in my experiment, find its mechanical energy 1 second after it's been released. I don't want to ask this question, no time. But if you read this problem literally, yeah, if we are told where the origin is, it's very simple now. If we didn't have information about the origin, we couldn't say a word about gravitational potential energy. First, we must choose the origin. So when the origin has been chosen for us, it's here, and the ball is released from rest. Where? Well, now this is up to us. If we assume it's been released above, the initial potential energy would be positive. If we assume that it's been released at this level, the initial potential energy would be 0. Here it would be negative. So now we have to make our second important choice. Where do you want to? Well, I wanted here. If it's released from rest, the initial velocity is equal to what? 0. And if my initial level, initial height is 0, what's going to be the kinetic energy equal to? Kinetic energy initial will be equal to what? What do you think? m0 squared over 2, 0. Potential energy initial will be equal to what? M times g times 0, 0. So the mechanical energy for this situation will be equal to what? 0 plus 0, 0. But that's the initial. Now, what does this tell us? That it stays the same. So 1 second after, 10 seconds after, billions of seconds after, well, if it keeps falling, it's still got to be equal to 0. How can that happen? Well, because when we're calculating the energy, well, kinetic energy is always positive, but potential energy depends on our choice. For this choice, 0 initial, when it's falling down, this term always will be negative and always will be canceling out the kinetic energy. A race car starts from 10 meters per second to 50 meters per second, traveling distance of 3 meters. Okay. So now the initial speed is not 0, it's 10. And the final speed is not 0, it's 50. The distance traveled is 3 meters. The mass of the car is 25,000 kilograms. There is a force of resistance. Well, we use this term to describe all combination of things which try to slow it down. Air resistance, deformation of the wheels, friction in the engine, doesn't matter. So that's compound number for all possible ways to slow it down. Find the average force which propelling the car. So of course, there is a force which makes it speeding up. And of course, we have two options. Option number one, because we know the initial speed, the final speed, the distance traveled, we can calculate acceleration. If we know acceleration and the mass, we can calculate the net force. If we know net force, we can calculate the applied force. We can use that logic. But now, let's use a different logic. Let's use the energy consideration. And in this situation, well, what can we do? We can start from writing the work-kinetic energy theorem. Final kinetic minus initial kinetic should be equal to the total work. Hence, 2,500 times final speed squared divided by 2. That's the way we're calculating final kinetic energy, minus 2,500, same mass, times the initial speed, 10. Speed squared divided by 2, supposed to be equal to. Well, it is useful to see all the forces. Yeah, okay. But gravity doesn't do any work. Normal force itself doesn't do any work. The applied force does. how do we calculate the work which would have been done by the applied force? Because it's a constant force, we can apply the original equation for the work done by the constant force. Magnitude of the force times distance traveled times cosine of the angle. Well, between the force and the displacement, yeah? Delta x. They both parallel. The angle is 0, cosine of 0 is 1. Plus, now we need to calculate write down the expression for the work done by the friction. We know it's -1, which is a cosine of 180, times the magnitude of the force, which is 120, times the distance traveled, which is 3. If we look at that equation, there's only one unknown. That's the very force we have to find out. We just use a calculator now and calculate it. A very common situation related to many problems when an object changes height. This is one of these problems. Or a ball tossed, or a pendulum on a string, or a roller coaster. They all are solved using exactly same strategy. For all problems like that, the most convenient approach is using the law of conservation of mechanical energy. In all those problems, normally friction set to 0, and if there is no friction, in that case, mechanical energy doesn't change. So if there is friction, my advice, use work-kinetic energy theorem. If there is no friction, use the law of conservation of mechanical energy. It's just more convenient. So the mechanical energy 1 should be equal to mechanical energy 2. Now we can apply the definition of mechanical energy. Kinetic energy 1 plus potential energy 1 should be equal to kinetic energy 2 plus potential energy 2. Now we should look at the picture. Even we see the height has been measured from the bottom of this gorge. I would say let's set up the origin at the lowest position of an object. Lowest. Here. So that's my origin. In that case, my final y, y2 equals 0, and my y initial will be equal to -70 minus 35. So that's difference. 70 minus 35. Against 35? Okay, that's a coincidence. Anyway, will be equal to 35. So now I can start writing numbers. M, I have to write a letter. There is no information about the mass of this guy. But I can't just have an empty space, so I have to fill it up with a letter. No. It doesn't have to be a letter. It can be anything. Any symbol will do. So today I want to use a star. This star represents the mass of this object. So we have to stick to this meaning. That's it. Times the initial speed, 38 meters per second. We have to square it divided by 2. Plus the initial height. So the mass times gravity times 35 meters should be equal to the mass times final speed squared divided by 2, just a second, plus 0. We can see that the mass getting canceled. And the final speed turns out to be equal to square root of 38 squared plus 2 times 10 times 35. And this solution gives the answer much faster than all other solutions. Thank you very much. Yes. Does the sign have any hints? Let me. Do you remember the picture you used for this? That's what you have to do. You have to draw the picture. You can use a board. You can draw the picture on the board. I need to see your picture. Yes. 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 So. Yes.
You know how like the first exam is 20% and the second exam is 21? Because of my situation, would you be able to, could you make the first exam 15% for me and the second exam count more since I would have been here to review all the material?
No.
You can't do that?
What I can do, I can postpone your exam because if you start it later, so I sent you an email about that before the lecture. Did you see it?
Let me check my calendar. I got your email about being able to postpone our homework.
Yeah, after that,
Oh, okay, yeah, I just got it. Hold on. I have to ask.
So the small is acting on the big, and the big is acting on the small. And the action is friction in both situations. So the static friction acting from the big one on the small one. So the same magnitude, but opposite direction to the static friction acting from the small one on the big one. So friction happening here, friction happening here. You go back here.
把这个力分解了嘛，这里合力了。那然后在这个 y 轴上，这个石头是平衡的。这个是等于这个。
I got it. I need this. I did. But here, thank you. Just a sec. So you have the force acting from the bench on the bottom box, right? This force. Force of kinetic action. Right? This is action. This force is action on the box number 1.
Which is the lower box.
Right. Here, there is a force acting. Number 1, that's number 2. Here, there is a force acting like this from 1 on 2. But here, also there is a force acting like this from 2 on 1. That's Newton's third law. So the red arrow belongs to the free body diagram for the top box. But the blue or the black, they belong to the free body diagram for the first box. And you also can draw a free body diagram for the whole thing. The whole thing this is just this. Gravity, pushing force, normal force, and this frictional force, which is the same. Force of friction here, here is the same force of friction. But we just have to calculate the difference depending on the situation. So if we do it like this, the force of friction will be equal to the coefficient times total mass times G. This is total mass, 1 plus 2. Right. For this diagram, that's what I said today. If we want to calculate this force, kinetic friction, we have to, well, this is because this force is equal to this force in magnitude. We always keep in mind that we start from the same relationship, force of equal to coefficient times normal. So I have to write exactly the same relationship here, coefficient times normal. Now, for this box, what we have? Gravity, M1, G, M1, G. Applied force. Well, it's string. We should this way. Now, this force doesn't disappear. It is a part of the free body diagram, but one force was missing in my calculation. Normal, and this, I don't know, it's kind of normal. Different force.
So I'm talking about calculating this one up here. Is this the static friction?
This is the static friction. But you calculated, and you can calculate only using this free body diagram.
You can't use it for the top one. So it would be just the normal force times the coefficient.
Calculate this force, you have to